Okay, today we're doing lesson 18b, which is on anti-differentiation. So let's say if we know the rate of change of y, so in other words dy dx, which is also obviously the derivative of y. And if we want to find y, we need to go backwards and find the function whose derivative is dy dx. So that is called the antiderivative. And the process of finding the antiderivative is antidifferentiation. So for instance, it's probably easiest seen with an example, one that we can do in our head. Dy dx, let's say that that's x squared. So if we want to know what y is, we have to think what function would have a derivative of x squared. So we know, and we've talked about this before, I think, we know that it's going to be a degree higher, so it's got to be x cubed. But if you took the derivative of x cubed, you would get 3x squared, and we want dy dx to be x squared, so we have to adjust this by dividing by 3, or multiplying by 1/3. So, but we've also discussed the fact that this doesn't tell the whole story, because any function 1/3 x cubed plus a constant will have a derivative of x squared. So we have to add the constant in to consider all the possible antiderivatives. And I know we've discussed this a bit before as well. So on the next slide, let's do a little definition here, a little write-up. So if big F of x is a function where the derivative of big F is little f, then the derivative of f, yeah, I just said it, then the derivative of big F is little f. That's exactly what this statement is saying. I'm just saying it in words here. And the antiderivative of little f is big F. So big F is the antiderivative, and the IB book and the AP Calc book both use big F for the antiderivative, so that's pretty common notation. The antiderivative, I find it helpful to remember it's the function whose derivative is f. Or actually, yeah, the antiderivative, the function whose derivative is f. So sometimes it can get confusing on what's what. And if you just memorize that the antiderivative is the function whose derivative is f, then hopefully that'll help you sort things out. Now we'll do some examples. So example 3 is where we're at right now. It says find the antiderivative of letter A x cubed. Oh, well, that we practically just did one just like that, didn't we? So the antiderivative will be, we'll call it big F of x, is the function whose derivative is x cubed. So that I know it's going to be x to the 4th, but I'm going to have to compensate for the fact that when I do take this derivative, it'll be 4x cubed, so that means I'm going to have to divide it by a fourth, or by 4 I mean, and plus a constant. We've talked about the plus a constant before, but just I guess I could mention it again, because x to the fourth over 4, well, the constant shifts the graph of x to the fourth over 4. So if it's shifting vertically, let's say x to the fourth over 4, that's probably something like this. That's what that would look like. Any vertical translation of that graph is going to have the same derivative. So that's why we have to add the plus c, because we have to consider all the possible antiderivatives. And I'm actually looking in the book here, and they did not add the c, which I find interesting, because you should always add c. So I don't know what they're thinking. Please add the plus c, because it is correct to do so. Letter B. E to the 2x. So we're trying to find big F, which is the function whose derivative is e to the 2x. And it might be helpful to remember the derivative of e to the x. So I'll do that over here on the side. The derivative of e to the x, since we memorized those, is e to the x dx. We actually memorized e to the u. Yeah, I'm going to fix that because that's how we memorized it. E to the u. So the derivative of, here, let me get the notation correct. The derivative of e to the u is e to the u du. So in this case, we know that the derivative of e to the 2x is going, or the function whose derivative is e to the 2x is also going to be e to the 2x. However, if you go backwards and differentiate this, so if I differentiated the e to the 2x, that would be, I'll write it, derivative of e to the 2x with respect to x would be e to the u times du, which is times 2. So that would be the derivative, but we want our derivative to be e to the 2x, so that means we have to compensate by dividing by 2. So this e to the 2x, we have to divide it by 2, and then plus the c. Now, both A and B lead us to a couple of properties. I noticed the IB book is not telling you those, but I'm going to because it just makes life so much easier. So let's do that on the next page. The antiderivative of, number 1, x to the n is, you're going to go up a power, so it's going to be x to the n plus 1, and then I'm going to switch back a page here. Notice we added, so the 4 would be the n plus 1, and then we're dividing by the n plus 1. So it's x to the n plus 1 over n plus 1 plus c. And that's the power rule for integration. Well, it's an antiderivative. And then the antiderivative of, and the way we haven't quite, have we introduced this notation yet? I've forgotten where I'm at. Have we done the integral symbol? Let me check. Oh yeah. So we could write this, the integral of x to the n dx. So the integral of e to the kx dx is, and I can go back to help you out here. So notice this would be like e to the 2x is over 2. So if I have e to the kx, it'll be e to the kx over k. Plus c. So those are a couple of antiderivative rules that you might want to keep in mind just to make life easier. And then we have one more example here. Find the antiderivative of 1 over root x. So, and essentially what this is this is what we're doing really. So on this one I would recommend rewriting it as x to the negative 1/2. We'll go ahead and use the calculus notation here. And it's just a power. So it's the power rule. So you're going to have x, you're going to add 1 to the the negative 1/2, which is 1/2. And then you're going to be dividing by 1/2. Add c. Now dividing by 1/2 is the same as multiplying by 2. So it's going to be 2x to the 1/2 plus c. And that's the same as 2 root x plus c. And that concludes section B. So now, moving on, section C, which is longer. It's the fundamental theorem of calculus. This is a really important theorem. It's a big one in AP Calc. We spend quite a bit of time on it, and it's very important. And if I excuse the pun, it is integral to the study of calculus. What it is it connects differential and integral calculus. And it was quite an accomplishment when Newton and Leibniz figured this out. It was, yeah, pretty monumental. Okay. So it looks like, oh, kind of just checking my notes here. So there's, in the blue box there, it says if, I'm just repeating what's in the book here. If f of x is a continuous, and they've actually got it as being positive, so okay. If f is a continuous positive function on the interval a to b, I'm going to use interval notation, then the area under the curve, this is weird. Didn't we already talk about this? Anyway, the area under the curve between x equals a and x equals b is the integral from a to b f of x dx. I feel like we've already talked about that. Let me check. Oh, yes, we did. Yeah, we talked about this back in section A. Oh, yeah, it says we've already observed that. Okay. Well, it doesn't hurt to go over these things a couple times. So there's a picture for it, which is going to lead us into this investigation, which I found rather interesting and quite useful. Now, ideally, we would do this in class, but we don't. It's not going to really work out so well for us this year, since we have AP as well. This is investigation 2. So I do ask that you follow along and try the problems. Maybe even sit down with the book and go through this and try it on your own. Then watch the video, because you'll get more out of it if you try it on your own before you watch me do it. So in this investigation, at the beginning, we're considering the constant function f of x equals 5. Okay, pictures are worth 1,000 words, so let's graph that. Let's call that 5. Actually, it goes on forever, both directions. And we wish to find an area function which will give the area under the function between x equals a and x equals t, is what they're using. So we want to find this area here. And so, of course, you could do it by hand, but we're going to do it using some calculus. So, still have the cold. A of t, in other words, the area under the curve, we'll use the integral notation. It's going to be from a to t of the function f of x, which in this case is 5 with respect to x dx. By the way, when you're writing your integrals, you have to put the dx on there. If you just write it as integral from a to t of f, it looks naked to me. I mean, you need to have the dx because it's your constant of integration. It's necessary. The integral symbol and the dx go together. You need them both. If you don't have the dx, you're going to lose points. So this integral is the area under the curve. Well, now let's use common sense and figure out what that area would be. So it's a rectangle. It's going to be length times height. The length is t minus a. The height is 5. And so if you distribute, you get 5t minus 5a. Notice that we could write this. So notice here you have f of x, which is 5. What would the antiderivative of 5 be? Well, the antiderivative is the function whose derivative is 5. So that's going to be 5x plus c. I'm going to drop the plus c for a second. Well, what happens here when you have 5t right here? That is big F of t, isn't it? Because if I plugged in little t into big F, I would get 5t. And then over here I've got minus 5a, which would be minus, whoops, that's supposed to be f, minus big F of a. That's a key connection right here. So let's move on to the next one. Oh, so what I did is I just did the first little part. So now it says what to do. Number 1, what is the derivative? Okay, well, we'll move on. So investigation, number 1. What is the derivative, big F prime, of the function when big F is 5x? How does this relate? Okay, so the derivative of this is obviously going to be 5. How does this relate to the function f of x? Well, we saw f of x is 5. So in other words, the derivative of the antiderivative is just f, the little function f of x. Okay, so that answers number 1. Number 2. Consider the simplest linear function, f of x equals x. Let's hope I have room. Okay. I'll put a few tick marks on here. Hopefully you've tried this on your own first. So this is f of x equals x. And again, we're going to go, oh, I didn't really need these ticks, I guess. We're going to go from a to t again. So let's make an arbitrary a and t. We're going to be finding this area underneath the curve that's bounded by those regions, or those lines. And so again, the area of the region, the shaded region, will be the integral from a to t of the function, in this case x, dx. Okay, now again we're going to use geometry to figure this out, and it's going to work nicely to use, it is a trapezoid, so let's use the formula for the area of a trapezoid. Area of a trap is 1/2 the height times b1 plus b2. So the height of the trapezoid is from a to t, so that's going to be t minus a. And then b1 would be this height, and b2 would be this height. Or I shouldn't probably say the word height, but anyway, it works. So area of trapezoid is going to be 1/2 times the height of the trapezoid, which is t minus a. And then b1 is this height here. And what would that be? Well, I know that that occurs when x is a, so I can plug a into my function and get the y-coordinate, f of a. So that's going to be simply a in this case. And then this height will be f of t, which in this case is simply going to be t. And we're adding those together. So now what we want to do is simplify this a little bit. And, oh, wait a minute, let me see. I might be getting ahead of myself. So question A says, can you write the area, oh, that should be a t there. Can you write it in the form big F of t minus big F of a? Well, what is big F of t? Well, that's the antiderivative of x. And we know how to find that. That's going to be used in the power rule. You're going to add, so normally it's x to the 1, and so you're going to add 1 to that and then divide by the new exponent. So it's going to be x squared over 2. So this would be x squared over 2. That would be the antiderivative. And we're going to be evaluating that at t. So we're trying to find t squared over 2 minus, and then big F of a would be plugging a in, a squared over 2. Can we manipulate this area equation so that it looks like this? That's our challenge. Well, I see I've got t minus a here and I've got a plus t. That's looking a bit like difference of squares. How about I rewrite this as, I'm going to go to a new color. Boy, those colors just don't switch very well. We'll do blue. We could write this as 1/2 times, and instead of, okay, I'm going to keep the t minus a. I'm going to write the other one as t plus a instead of a plus t. Now, let's distribute that, and we know that that's a difference of squares. It's going to be t squared minus a squared after we distribute. Ooh, it looks like we got it. Distribute the 1/2, we're going to have t squared over 2 minus a squared over 2. So a little bit of fun algebra, and we got them to match. So then letter B says, if so, what is the derivative of big F? Okay, so big F in this case is x squared over 2. So right now I'm doing part B. So big F is x squared over 2. So the derivative of big F would be 2x over 2, which is just x. And lo and behold, that's our function, because little f in this case was, where did it go? Right here. Little f is just x. So this is f of x. So again, we're seeing that the derivative of the antiderivative is just the function. So derivatives and antiderivatives undo each other, is what we're seeing here. Okay, next we'll do number 3. So this time we have a new function, and this time it is 2x plus 3. If you haven't done so yet, I would say pause and do this one on your own, and then come back and see how I work it. So this time our y-intercept is 3, and we have a slope of 2. We're still going from a to t, so some a value, some t value. We're looking for the area under the curve again. And we're going to set up the integral. It's the same thing again, just getting a little more practice, just seeing this thing over and over again until we really feel confident of the pattern that we're finding. Integral from a to t of 2x plus 3 dx. And so, next we're going to do, just like we did before, we're going to find the area using geometry. So again, it's a trapezoid. It's going to be, the area using geometry is going to be 1/2 times the height of the trapezoid, which is still t minus a, times b1 plus b2. So b1, the height of b1 is going to be f of a. Height of b2 will be f of t. So that means I'm plugging a into my function to get the height. So that's going to be 2a plus 3. That's the base 1. And then base 2, so I add base 2. Base 2 is going to be 2t plus 3. And then it's going to ask us, just like before, can we rewrite this? Can we write a of t in the form big F of t minus big F of a? So that's where we get to do the fun part of the algebra manipulation. Oh, first of all, let's figure out what big F and what big F of x is. So here's little f of x. Big F of x is the antiderivative. So we could use the power rule here. X is to the 1, so we're going to add 1 to that, which is 2. And then we're going to divide by 2, but there's already a 2 out front, so it's just x squared. And here we don't have a power, so if we just if you kind of think about it, the function whose derivative is 3 would be 3x. Okay, so that's big F of x. So we're trying to manipulate this so that we have f of t. So in other words, we're going to have t squared plus 3t, that's f of t, minus f of a. So plug a into big F, you get a squared plus 3a. Or in other words, t squared plus 3t minus a squared minus 3a. That's what we're shooting for. So we need to manipulate this equation here to get it to match this equation. Okay, let's do it. So we're going to bring this down. I've got 1/2 t minus a. So I'm going to combine my 3's. That's just the logical thing I would see next. And I'm thinking, let's go ahead. I want to distribute the 1/2 over here and knock these 2's down. So I'm distributing the 1/2 to all these. So I've got the t minus a. That's going to be a plus t plus 3. I just did that because I want to get rid of that 1/2 and simplify things a little bit. And you don't distribute to both of these, you only distribute to one of them. Because if you distributed to both, you'd be multiplying the whole thing by 1/4 instead of 1/2. Now we'll distribute this all out. So I'm going to have at plus t squared plus 3t minus a squared minus at minus 3a. And I see we have at's cancel out. And now, oh, it's looking pretty close. I've got t squared plus 3t minus a squared minus 3a, which is exactly what we were trying to get. Pretty exciting. And it says, how does it relate to f of x? So again, if you take the derivative of big F, which I have up here, I'll come back up here again. So if I do the derivative of that, I'm going to get 2x plus 3, and obviously that's also f of x. So again, the derivative of the antiderivative is just little f. Number 4, you repeat it again. Let's just go ahead and skip that. I'm hoping you're seeing that we're getting the same result every time. So on number 5, you could try that one on your own. And it says predict what big F would be without performing the algebraic procedure. So do that on your own, and then I'll just give you the answer here on the next slide. Okay, so there's little f, and then big F would be the antiderivative. And so you're going to use the power rule. You're going to get x to the third plus 2x. Well, so it's going to be 4x squared over 2, which is 2x squared, plus 5x. And I don't have the plus c on there. I really should put it on there. Although I don't think we didn't on the other parts of the investigation, so we'll just skip it for now. So that was the investigation, which I really liked it because now you can see, well, you're going to see a couple of things. The two things we saw, well, let's talk about what we saw. So the first thing we saw is that the derivative of the antiderivative is f. There's another interesting thing we saw, though, again and again on this. I'll come back to the beginning one. When you're evaluating this integral, you're getting, where did I write it? Right here. This thing equaled big F of t minus big F of a. And that happened on the first one, it happened on the second one, it happened on the third one, because we saw that it says, can you write the area, which is the integral, in this form? And yes, we could, it worked. So this is also equal to the antiderivative at t minus the antiderivative at a. So let's write that up. The integral of f of x dx from a to b is the antiderivative at b minus the antiderivative at a. And that is a definite integral, by the way. It's definite because you get an actual value. As we'll see as we do some of these, you actually get a value. There is no plus c. An indefinite integral is the one with the plus c, where it can vary. So an indefinite integral looks like this. It's indefinite. When you evaluate this one, the indefinite integral, you get the antiderivative plus c. When you evaluate a definite integral, you're going to get an actual value. We'll get a value, which represents the area under the curve. Area under the curve, f of x. Whereas with the indefinite integral, you get a family of functions whose derivative is f. I write sloppy, sorry about that. Family of functions whose derivative is f. And this family of functions differs by a constant. In other words, they are all vertical shifts of each other. So that's the difference between a definite integral and an indefinite integral. They both involve the antiderivative. That part doesn't change. That's the same for both of them. Okay, I've only got 5 minutes left until my prep ends, so I better get moving here. What do we got? Let's check. So the fundamental theorem of calc, I pretty much just stated it, but let's write it down. And I'm going to check out the book here and see. Just hold on a sec. I want to make sure and write it down the way that they do it. I see it's here on page 450. Okay, so fundamental theorem of calc. There are a couple of parts, so the IBIC is not telling which one is which. So I'll just write down what they got here. If for a continuous function f of x with antiderivative big F of x, the integral from a to b of f of x dx is, as we saw in that investigation, which was so cool, it's the antiderivative at b minus the antiderivative at a. This tells you right here how to evaluate definite integrals, by the way. Super exciting, very cool theorem. And then with the time I have left, I've got 4 minutes left. If you look in your book at page 452, you're going to see a list of properties of definite integrals. And you'll be proving some of these properties in your homework so that you can see how you're going to go about proving them. We'll go ahead and do that example proof that they have. So the property that we're going to prove is, and I'm not going to take the time to write these down. I would like you to look in the book because they're all very important. You need to know them. And I would take time, but I'm running out of time. So, but do look at them on your own and write them down in your notes. So let's say we have the integral from a to b of f of x dx, and we're going to add the integral from b to c of the same function f of x dx. That is going to equal, and I can show you graphically, which this is not going to be the intention of the proof, but I think it will help you see what's going on. Let's say this is f of x, and so here's a to b. That's the first integral. It's going to tell us the area under the curve from a to b, so it's going to give us this area. And then the second integral is going to be from b to c. Oh, by the way, I don't know that I mentioned, but this is, I think I did mention lower bound and upper bound. So you're going from b to c. So here we'll put c out here. So now I'm going to add this first area to the second area. So what am I going to get? I'm going to get the total area from a to c. That's the easiest way to remember that property, just thinking about the graph. But they want you to actually prove it using the fundamental theorem of calculus. And don't worry, it's not that hard. All you're going to do is you're going to rewrite this using the fundamental theorem of calculus, which says that this is equivalent to the antiderivative at b minus the antiderivative at a. And then do the same for the next one. So plus, and then this will be the antiderivative at C minus the antiderivative at B. And then we can see that the f of b's cancel out. And we get, we're going to have f of c minus f of a. I'm going to write it that way. Big F of c minus big F of a. And then that's equivalent to going from a to c of f of x dx. So now on this last step, I'm using the fundamental theorem of calculus again, but I'm doing it in the opposite direction. And that proves what we were trying to prove. So that's how you're going to do your proofs of those properties in the homework. And now we just have one more example. I'm going to try to quickly do it in 1 minute. It says use the fundamental, this is example 4. Oh, hey, I have lunch next. I can do this. Yay. There's actually, 2 problems. Use the fundamental theorem of calc to find the area between, so we're finding area, and we've got the x-axis, y equals x squared, and x is 0 to x equals 1. So I always like to draw a picture. X squared looks like so. We're going from 0 to 1. So we're finding this area right here. Let's set up our integral. We're going from 0 to 1 of f of x, which is x squared dx. Okay, so this is going to be the antiderivative at 1 minus the antiderivative at 0, using the fundamental theorem of calc. Okay, what's the antiderivative? Well, we can use the power rule. We know that it's x cubed over 3. Now, I'm going to show you a notation of how to write this. We do a vertical bar, and we go from 0 to 1. So this is how, we don't really write this part out, I just shown you what we're doing. Down here, this is how you write it. So this means evaluate at 1, so 1 cubed over 3 minus 0 cubed over 3. And that is equal to 1/3, and it's area, so it's units squared. Next, we'll do that was part A, example A, and then example B. It's interesting that I'm looking at the IB book, they don't use that same notation. I think they should, but anyway, that's my opinion. Letter B. This time it's again the area between the x-axis. This time it's y equals root x, and x equals 1 to x equals 9. Okay, let's draw a picture once again. Root x looks essentially like so. There's the bell, but it doesn't matter. Going from 1 to 9. So we're finding this area right there. Sets up the same as always, integral from 1 to 9 of the area under the curve, so the function, root x dx. Okay. The good news is we know the we can use the power rule again on this one, because you can write this as the integral of x to the 1/2 dx. And then you can add 1 and divide by the new. So 1/2 plus 1 is 3/2. Dividing by 3/2 is the same as multiplying by 2/3.
Heavenly Counter,
And
please come to the front office.
we're going to
Eric Moss, Jeff Flynn, Josiah Albert, Mallory Bradford, Matthew Daniels, Sarah Baton, please come to the front office.
okay. Evaluating that from 1 to 9 is how you say it, equals. We're going to be plugging, oh, by the way, there's a 2/3 out front, so I'm just going to write that constant out front and put a parenthesis. That way I don't have to put it through every time. X, so I'm plugging in 9 for x.
Club today, so if you're involved in that club, there is a meeting today.
Great. Okay, then plugging in 1. Okay, and then we can do 9 to the 3/2 in our head. The easiest way to do that is do 9 to the 1/2 to the 3rd. So the square root of 9 is 3, 3 cubed is 27. I'll bring down the 2/3, and then 1 to the 3/2 is simply going to be 1. So then we're going to have 2/3 times 26, and that does not reduce, so twice of 26 is 52 over 3, and it is area, so it's units squared. And that concludes section C. I hope you enjoy this. I think it's a lot of fun. I hope you guys do too.